Hello everyone and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina and I would like to introduce our speaker today, Mauricio Gago, who will be speaking about a very interesting topic, synergetic effects of particle and transient heat loads on ITER-grade tungsten. Our speaker today, Mauricio, has completed his bachelor degree in chemistry in the University of Costa Rica. He then obtained a master's degree in materials science from the University of Stuttgart. And 2017, he started his doctoral studies in Jülich in Germany, and he's still currently working there, studying and testing materials for the ITER divertor, as well as for future fusion reactors. So without further delay, I would like to give the floor to Mauricio.
Yeah, so good afternoon, everyone, or good morning, or good evening, depending where you are. So yeah, as mentioned, I want to talk to you today about my research on the effects of particle and heat loads on ITER-grade tungsten. So I know most of you already work in fusion or have studied it, but for those of you who don't or who are new in the field, ITER will be the largest fusion reactor in the world and is currently being built in southern France. It should start operations sometime in the next few years, and it will be several times larger than JET, which is currently the largest fusion reactor. You can see a size comparison here. So this is JET, and this is what ITER will be. And it is expected for ITER to produce 10 times more fusion power than heating power than the heating power it consumes, being the first reactor to have a net power gain. Inside the reactor, we will have the plasma being contained, which will be at around 150 million degrees C. And in order to regulate these hidden particles inside the reactor, the magnetic field will be configured such that excess particles and heat can be extracted by causing them to hit the zone here, which is known as the divertor. This will cause the divertor to be the area where the plasma-facing materials are exposed to the highest loads inside ITER and inside most reactors, in fact. So because of this, we will have very high loads. And this requires the material that is used for this, the plasma-facing material, as it would be called, to comply with strict requirements, such as, first of all, having a high melting temperature and a high thermal conductivity, having a low tritium absorption and the sputtering yield, being available and not being too expensive, such that it would be prohibitive. And also not producing any long-lived transmutation products, which is also important so that we don't produce as much radioactive waste as possible, and that we can also store it only for 100-200 years, and then it can be reused. And of all the available materials, tungsten is the only one to comply with all these requirements. And it is therefore the material chosen as plasma-facing material for the ITER divertor. So once inside ITER, we will have very high heat loads. ITER will function in pulses, basically of around 400 seconds. And during these pulses, we will have slow transient events, which will have from 5 to 20 megawatts per square meter of power load, of power density, actually. And then we will have also regularly edge-localized modes of up to 1 gigawatt per square meter. And it is expected for there to be millions of these events during the lifetime of the divertor. Also, some off-normal events are expected to occur, such as vertical displacement events and disruptions seen here, which this can also be mitigated in some ways. But for now, we will concentrate on mainly on the ELMs, which are expected to be the loads that will affect the divertor the most. So I like putting these numbers into perspective. And first of all, we will have highly energetic neutrons and plasma particles that can modify the lattice structure and the composition of the material. Aside from this, the slow transients produced during normal operations in ITER will subject the divertor to up to 10 times the loads as in a spaceship re-entering Earth. And additionally, we will have the transient loads that I mentioned before from the ELMs, which will increase the surface temperature by more than 1,000 degrees in less than 1 millisecond. And so these are very, very high loads that we're expecting the material to sustain. And so what effects will these kinds of loads have on PFMs? So depending on how the materials are tested, the results can be very different. As we see here, we have one tungsten sample tested with laser and plasma, which is very similar to what I will show you afterwards in my results. In here, we have the synergistic effects of both. On the right, we have a sample tested in similar conditions under an electron beam, but in this case, it's only heat loads that were applied. Of course, between laser and electron beam, there are certain differences, but we can see also very clear differences if it's with plasma or without plasma. And these kinds of effects we would like to understand more clearly. So what we do know now is that these loads can lead to a degradation of the mechanical and thermal properties of the material, but the long-term fatigue behaviors, these are still not fully understood. They lead to embrittlement, to a decrease in hardness, or an increase in hardness, as we will see actually, depending on the area that is analyzed. And they can also increase fuel retention and erosion of the material, which is undesirable. So to better understand how PFMs, or plasma-facing materials, in the ITER divertor will be affected, we need to simulate the conditions inside the reactor as realistically as possible. But up till now, no device can completely simulate the loads expected in the ITER divertor. But we can get close, or at least as close as possible. So in this case, the linear plasma device, PSI2, was used. It can generate stationary plasma loads, so it has a plasma source. Here on this side, here we have some magnets which can cause the plasma to hit the sample here. And additionally, we have the neodymium YAG laser, which can reproduce the transient heat loads, which will be caused by ELMs. We can see here a sample being exposed in the device. Yeah, and then the laser impinging it on an angle. So for these tests, we will use tungsten samples, which are ITER-grade. So it's basically the material that will be used, or very similar to the material that will be used for the ITER divertor. And from the original tungsten rod, depending on how the samples are cut, we can either obtain microstructure which is needle-like in two different directions, either transversal or longitudinal. For these experiments, because the transversal microstructure is preferred for ITER because of its cracking properties, this one was selected. And because under the conditions for the ITER divertor, the material might recrystallize due to it being at very high temperatures for certain amounts of time, it might recrystallize inside the divertor. So we wanted also to test this kind of material. And yeah, so for all the tests, to make them comparable, a base temperature of 700 degrees was used. This is also approximately, or at least a relevant temperature for the ITER divertor. Then deuterium helium plasma was applied with a mix with a 6% helium, which is also once again relevant for ITER because this is close to the percentage of helium that will be expected once the reactor is fully functioning. And for the laser pulses of 0.5 milliseconds were used, which is close to the pulse length of an ELM. And so I would now like to give you an overview of the effects of ELM-like events we'll have on the material, depending on the power load applied. This will be done simultaneously with the plasma loads first. And we can see first that if we only apply plasma, the sample surface is not really damaged, but we see the formation of what is known as tungsten fuzz. So these thin filaments. And this is important because it's not clear how much it might affect material behaviors, in particular erosion, because if we have these thin filaments, then it is logical to think that these might break off or enter the plasma somehow more easily. Also, the heat dissipation in these filaments will not be the same as in a bulk sample. So this is also important to know. Then once 100,000 laser pulses were applied of 0.2 gigawatts per square meter, we can already observe here that there are cracks being formed and the surface has been roughened. And we still see some of the tungsten fuzz being formed here. Also the roughness of the surface. We can see here that previously it was much lower than when the laser pulses were applied. And we can see the laser spot here very clearly. And outside the laser spot, the surface was actually not really affected that much. Now the power density was increased. Everything else remained similar. And we can see already a very large crack network being formed and pores being formed in the surface. Another important fact to observe is that we don't see any more tungsten fuzz being formed here. And then getting closer to the power density expected for ELMs, we see that the cracks have become larger. There is a clear swelling in the surface of the sample, and the bubble formation increased. So the bubbles that are observed are actually larger than before. But also there is local melting that can be seen. I don't know if you can see it in the image, but there are small spheres or sphere-like formations on the surface. And this is clearly an indication that at some point these some parts of the material were melted. And if we have melting on the surface, it means that the temperature reached the melting temperature of tungsten, which is around 3,400 degrees. And this is also not desirable because it will mean that the material can sputter more easily, or that the behavior of the material or its properties will degrade much faster. Then, to have a comparison between the transversal, well, actually, I want to, yeah, here we will have different comparisons, because first, I will show you the samples exposed to only the laser without plasma, but also I will show you the samples, the transversal samples and the recrystallized samples. So I know it's a lot in one slide, but yeah, just let's go step by step, and then yeah, I hope it's not too cluttered. So we can see that first, with the lower power loads here, there is a almost no cracking, maybe some cracking can be seen, a low surface modification. Also, no tungsten fuzz is formed, because tungsten fuzz forms only when plasma is applied. So here yeah, it was not really expected. And then the cracking network begins to form once we increase the power load. And when we increase it even more, then actually something interesting happens, that there are actually no cracks in the center of the laser spot, but only on the outside, which was something not observed on the, yeah, with 0.4 gigawatts per square meter. It is expected that the cracks start on the edge of the laser spot, because here the temperature gradient is larger. But why they didn't form in the center, this is maybe harder to explain. But also we see that there's more cracking than before. For example, in some cases, which is an indication of, yeah, hydrogen embrittlement, which we will see now that we have recrystallized versus transversal as well, but with a low flux of hydrogen helium plasma applied. So here, one interesting thing to observe is that at the lowest power load, we have almost no surface modification for the transversal sample, and then and we have a much higher surface modification for the recrystallized sample. This I will explain to you at the end of the presentation, because it has to do with some other phenomenon that we will see. But once we applied 0.4 gigawatts per square meter, we see that the recrystallized sample actually has a higher resistance, at least in this case. So it is also important to mention that only one sample was tested per condition. So of course, there will be a high variability, and ideally more samples would be tested per condition, but because of limitations with the time that it takes to test every sample, then only one was tested. But we can at least see that in this case, the recrystallized sample was more resistant than the transversal one. And then at the highest power load, now we again see that the crack network forms throughout the sample, and not only in the center, not only on the outsides of the laser spot. And this is now a more clear indication that hydrogen embrittlement, or hydrogen and helium embrittlement even, has happened. And if we increase the plasma flux, then we see some other effects taking place. So increasing the plasma flux and comparing it between high flux and low flux exposure is very important, because in ITER, the total fluence is expected to be several orders of magnitude larger than the ones with which we tested these samples. And this means that any effects brought by the exposure to plasma should be expected to be exacerbated during full DT operation. So deuterium-tritium operation. So this means once the reactor is actually functioning in its full capacity. But we can already see that there are some differences between these two fluxes or fluences. So here we can compare them more closely. We see that at the lowest power load, for example, here and here, and here and here, between low flux and high flux, the fuss formed is actually much higher, or at least much longer for the high flux samples. And at the highest power load, if we compare the size of the bubbles or the pores that are being formed, we can see that the pore size is much larger with a higher flux. So this means that if the fluence is several times higher in ITER, that the pores could be expected to be even larger. So this is also an important factor to take into account when we want to analyze how the material will behave. And then another process that is having place during the tests is that of recrystallization. As I mentioned before, it is expected in the PFMs, and we can see that during these tests as well, on the areas affected by laser, recrystallization is taking place, and this does not happen in the areas affected only by plasma, for example. So it's merely an effect of the heat loads, and especially that the areas affected by the laser at higher power loads, or at 0.4 and 0.8 gigawatts per square meter, the surface temperature increases, and at some point during the temperature peak, and the temperature of the samples is higher than the recrystallization temperature of tungsten, which is about 1,300 degrees C. And we can see that there, also because of the plastic deformation that is taking place during this expansion and contraction, there are different effects taking place, such as grain nucleation, as I said, plastic deformation, and also recrystallization. So we see a lot of smaller grains being formed in both samples, and then also some larger grains being formed, especially in the surface, also even at the kind of lower power loads. Now, as I mentioned also at the beginning of the presentation, the amount of ELMs expected for the ITER divertor during its lifetime is in the millions of events. Up till now, I have only shown a number of pulses of 100,000, but then it's also interesting to know how PFMs will behave after a higher number of ELMs. So also due to time limitations and the limitations of the frequency of the pulses had to be increased, and because of these, if a higher power load was applied, and the temperature of the samples would increase way too much, even the base temperature. So this wouldn't have been able to stabilize. And then a power density of only 0.2 gigawatts per square meter was used. So only the lower power density that has been used up until now for these high pulse number tests. But still, this is very important because one of the plans to mitigate the effect of ELMs is by ELM pacing, which means that ELMs will actually be happening more often at a higher frequency than for unmitigated ELMs, but they will have a lower power load. And so if they deposit a lower energy per ELM, this gives time for the material and for the cooling system to dissipate the heat, and then the material will not remain at higher temperatures that much. So for these tests, we see that after 1,000,000 pulses, with only laser, we have already a crack network. We see surface modification as well, but the cracks are still very thin. And then once we apply also plasma to this, then we see the effects of hydrogen embrittlement in that the cracks become also broader. And then we see already some small pores on the surface. But then again, also this time no tungsten fuss was observed, for example. And yeah, but no really large cracks were observed as in previous tests with higher power loads. Now, another phenomenon that was observed that I think is very relevant for PFMs in the ITER divertor is that of bubble formation. So on the surface, for the samples exposed to plasma, we could see that there are pores being formed. And if we perform a focused ion beam cut of the samples, we can see that there are bubbles being formed also underneath the surface. And we can see here that this doesn't happen when we apply only plasma or only laser. So this only happens when we apply laser and plasma. And as we will see later, so first, if in the samples exposed to 1,000,000 pulses even, so we also don't see any bubble formation here. This bubble formation we only start seeing at higher power loads. So at 0.2 gigawatts per square meter, we see no real bubble formation. So here we see only some of the fuss that has been formed. At 0.4 gigawatts per square meter, we already see small bubbles being formed on the surface, but they're not really that significant. And then only at the highest power load, which is close to the power load expected for ELMs right now in ITER, we see a significant bubble formation and also the bubbles being coalesced, and that's why they have a higher size. And we can expect this the size to be even larger with a higher plasma flux. As we saw, the pores also increase in size. So I would say that most probably the size of the bubbles also grows underneath the surface with a higher fluence. In these samples, we can already see that there's the amount of bubbles on the surface is very significant. Actually, analyzing this image, for example, we see that the bubbles occupy 3% of the analyzed area. And how this affects the material behavior, this is still not completely clear, but it can, if we have more pores, then this will at least affect the heat dissipation. And this is already very important because then the surface will always be warmer than expected. So as I mentioned at the beginning, when we saw that for some samples, the especially at lower power loads, the transversal samples have a higher cracking threshold than the recrystallized samples. This has also been seen in previous tests, and so here we tested via X-ray diffraction and with the sin squared psi method the residual stresses in the samples, especially in the laser spot. So here we have one sample which was covered in a copper foil. This is so that the signal of the outside the laser spot doesn't interfere with the signal of the laser spot. And we can see that the transversal samples here start with compressive residual stresses in the surface, and these compressive residual stresses, what cause is actually the sample to have a higher cracking resistance. But once power loads are applied, and these compressive stresses actually at first they turn into tensile stresses, which actually promote the formation of cracks. And after the power load is increased, so already when the sample surface reaches higher temperatures, especially temperatures higher than the recrystallization temperature, then all stresses are more or less relaxed. So we then don't see a big difference. And lastly, the hardness of the sample surface was tested after tests with the highest power load. So this was to see how hardness is affected by a combination of both loads. And we can see that at the top of the sample here, the hardness increases significantly. And then underneath the surface, some micrometers underneath, we still see the effects of the increase in hardness. And then it gradually decreases until we reach the bulk of the surface of the sample. And then where the hardness stabilizes, basically. And then we also tested the sample surface where only plasma affected the sample, and we can see that the hardness of the sample is the same as in the bulk sample. So the plasma by itself doesn't affect the hardness of the material. And this is important because hardness is actually normally connected to the brittleness of the sample. So this in part is because of the hydrogen and helium embrittlement. And yeah, this effect we can see clearly here. So to conclude, we expect tungsten phos formation at lower power loads. This means that phos will form in some areas of the divertor, and it also might increase material erosion. Then high heat loads increase surface temperature and allow bubble formation, and plasma fluence increases bubble size. So bubble formation should be expected in the divertor. This can hinder heat dissipation and perhaps even increase tritium absorption. And then recrystallization and cracking at expected ELM heat loads is to be expected, and mitigation of transient events might be necessary. Thank you very much.
Thank you very much for the very interesting talk. Okay, so I think the first one was Alessandro Tassone. Please go ahead. You should be unmuted now.
Okay, so hello, Mauricio. Thank you for your talk. So I have a question about what you said about the transversal crystalline structure for tungsten that is preferred for the divertor. Maybe it's something that you have already explained, and maybe I lost it, but I would like you, if you could expand a little bit for that, because from what I understand, the transversal crystalline structure has almost no plastic deformation, and I thought that that would be preferable to have some, let's say, plastic deformation in on the armor.
Yeah, so the reason why the transversal crystal structure is preferred is because if we have the longitudinal crystals, so I can maybe go back quickly, or not so quickly. Here. So when a crack forms here, so it goes basically, yeah, also perpendicular to the surface, right? And if we have a longitudinal microstructure, when a crack forms, it can form here, for example, and then it goes in this direction. And this forms a thermal barrier that makes it harder to, yeah, for heat also to dissipate. And this is why it's not really preferred. And then also it can break off more easily inside the divertor. So these are the reasons why the longitudinal is not preferred. I don't know if that's clear, or if you have, I don't know, another question about this.
Yeah, no, it was clear. What I was thinking is that since the longitudinal one has some capacity to, let's say, plastically deform, it's not more probable for the transversal structure to initiate cracks. So this is just what is confusing for me. So I will expect the transversal one to be more likely to generate cracks compared with the longitudinal one. I'm clear about the concept of thermal barrier is clear, but I have this doubt.
Yeah, so in previous tests, so the yeah, other also researchers have tested all three structures, and from what I know, no real difference in really crack formation has been seen between transversal and longitudinal. So I don't think if there is a difference, it's not really that significant, and yeah, it's in the end preferred for either, or that was at least the decision that was taken to use the transversal microstructure, just because of how the cracks, once they form, they yeah, they expand. Also because in the end, even if a crack forms until the cooling tubes, for example, it's not as bad as if a part of the divertor breaks off if the cracks are longitudinal. I don't know if there's another question, or if you.
No, it's okay. Thank you. It's clear.
Okay.
Okay, thank you. Next one, Davide.
Okay. Hi. So thank you very much for your clear and nice presentation. So my question is basically if you had, if you could give us any idea if how much your study affects the known ITER limits that are basically set for the ELMs on the energy fluence reaching the divertor. So like there are previous studies done on this, and so I'm just wondering how much those studies were including as well the interaction between plasma and yeah, as you were showing here, and yeah, how much your studies then can have an influence on that.
Sorry, can you repeat the question, because the beginning of the question I didn't hear completely.
In easy words, my question is if you think that your study, or what you showed us here, has an impact on the energy fluence limits that we know on the ITER divertor. If they maybe could be lowered, or if it has it's not a big deal.
To really know if it will have an impact, I cannot be sure. I would say so that if for example bubble formation wants to be prevented, so this really needs more research done on it, how much bubble formation, for example, will affect it. But definitely I would say that if this is to be prevented, then the power loads have to be decreased. Anyways, a lot of research is being done on how to mitigate the ELMs. and hopefully this will be effective. So, but yeah, whether this will be taken into account to decide that the power loads or this limit should be lower, it's hard to say.
Okay, thanks.
I see one more question from Guido van Oost. Please go ahead.
Okay, do you hear me?
Yes,
Yeah,
it's
yes,
fine.
I hear you.
Thank you for your clear presentation and for the interesting results. In fusion research, so a number of types of tungsten are being used, so-called tungsten grades. Are the results which you presented generally valid for the different type of tungsten grades?
Yes, this is ITER-grade tungsten, which also is basically the tungsten grade that will be used in the divertor, from what I understand. So it's only tungsten, it doesn't have any alloying material, which has also been one of the discussions, right? If titanium carbide or some other kind of alloying material will be used. But this is pure ITER-grade tungsten.
Okay, of course, after some time, after some plasma discharge, there can be a change due to irradiation, neutron irradiation. And is this something that has also been investigated, how these results can be affected by neutron irradiation?
In this case, not, because we are not able to test irradiated samples. But for example, there are being some tests done right now with, for example, tungsten with rhenium, which is the main transmutation product of tungsten, and how this will be affected. But right now, at least personally, I don't have the results right here to really know how this will be affected. And it's the missing component, let's say, on this research.
Thank you.
Yeah.
And I see there is a question from Dieter, please.
Yeah.
Hello, Kate. This is Nicolas Yelovega, actually. Dieter is just next to me.
Okay.
Oh, sorry.
Yeah, nice to see people here. Thank you, Mauricio, for a nice talk. Sorry, I missed like the beginning. That's why I joined not through my computer. I just wanted to comment a little bit on your talk. Like, be careful, because sometimes you say it's gonna you make some sometimes a bit strong statements, in my opinion, for ITER, but you have tested your samples in linear plasma device PSI2, which doesn't have, high flux, neither high fluence you cannot achieve. So you cannot really predict what's gonna be in case of ITER. Unfortunately, we don't have ITER at the moment, so it's really difficult to make predictions. I wanted to ask whether you have tested deuterium retention in these samples that you have. I'm curious if these tests have been conducted.
So not really methodically. I do know that in these conditions, because other colleagues have tested this, I cannot give you numbers, but I know that at these temperatures, for example, that we are using, the tritium or deuterium retention is very low. And actually, most tritium retention experiments, because of these, are done when samples are exposed at 200 degrees C, or more or less. But yes, as I said, I cannot give you really clear numbers.
Okay, thank you.
Well, I don't see any other questions for now, so I think we can have the official part of our webinar.